No, va bene. Grazie. Primo scusi perché il mio italiano non è buono, parlare l'inglese. So thank you for your chat before, because it's a very good introduction to what I'm going to tell you right now. And so I'm going to talk about the forensic analysis of pigments and inks by Raman spectroscopy. So you were talking about Raman and how important Raman is for philologists. And I do think it's really important. So I'm going to try to, in 30 minutes, to explain what Raman is and what do a chemist do with a philologist. Although we've been working with different disciplines, different like archaeologies and some other cultural heritage using Raman spectroscopy and also different techniques. I began saying pigments and inks because pigments are present in the human being since very early. In prehistoric times, the first pigments we saw were those in the rock paintings, as you can see here, as long as 27,000 years before the present time, using very simple pigments like iron oxides or manganese oxides, carbon black, sometimes some difference, but very simple pigments, 4 or 5 pigments, no more. And the first scriptures which we have studied are those here from the Sahara in Africa, which were made also with iron oxides and with, this is a Bereber script, who's the archaeologist doesn't know really what they wanted to say. It's a very primitive sculpture into rock paintings, okay? But I think the most important for you as a philologist are the inks over different surfaces or different materials, just as papyrus or ancient papers, parchment or leather, and especially paper, like this invoice here, which we are talking later, and the study of this invoice with Raman spectroscopy. But let's go to the beginning. Why is so important? You have made a very good introduction. Why is important a physical chemist analysis for pigments or inks? Because we can give you more information. Sometimes you have a lack of information, and what chemists can give you can make you, as you said, for example, complete all what you have thought about that text. So the first of all is a study of the historical context. Then we can identify the materials used to fabricate these inks. And I have to say, I'll tell you something later, but iron ferrogallic inks, not all of them are the same. They must be similar, but we can distinguish perfectly well if they have little differences in between. The determination of the manufacturer, and we can talk about time and location, which is very important. And of course, preservation of the manuscript. If we do know what kind of chemist compounds we have there, we can say how to preserve. So it's very interesting. What can we study due to this Raman spectroscopy technique? A few things. First, the support. It can be different supports like parchment, which means we are studying proteins, or paper, which means in a chemical language, carbohydrates, and of course the inks, which is one of the main issue of this chat. Color inks for illuminated manuscript that can be mineral or organic ink pigments, because there are a lot of pigments for studying. I mean, it's not just ferrogallic inks. There are a few more. And black inks, which are 2 types, carbon black and metal gal inks, because besides iron, we can find some other metals. And of course, some other materials like seals, textiles, metals, wood. Which are these techniques we are using or has been used in the in situ analysis manuscript? This is very interesting because, as you said, we have a portable Raman spectroscopy, which makes things easier for you. You don't have to move the documents from the museums or archives or the Vatican or libraries. So we can go there and study in situ the manuscripts, which is easier for everybody. How we can study it? There are different techniques, and each one of these are used for a different analysis. Infrared spectroscopy, which is a vibrating technique, used more for organic compounds. Scanning electron microscopy plus EDX, which is more for elementary. X-ray fluorescence, as you have been talking about, which is more elementary too. Raman scattering, which I'm going to point out today. And UV vis reflection absorption, which you have talked before. And the manuscripts we have been studying among these years were in Moroccan private collections from Morocco, the National Library from Spain, and the National Archaeological Museum in Spain, and also the National Archive, Historical Archive in Spain also. And I don't know if we have more or less in the Vatican, but there are a few documents there. Why Raman spectroscopy? Between all the techniques I've been telling you, why have we chosen Raman spectroscopy? Because it has a lot of advantages. The first of all is non-destructive, non-invasive. I mean, we do not destroy the sample, and we really do not destroy it, because it's light, and usually we don't even have to touch the sample. So that makes it very appropriate for cultural heritage. The second one is the selective identification of the chemical components. We can identify perfectly well from each other, even if they're mixed. And we only need a very tiny, tiny part of the sample to analyze, just as tiny as the laser beam, which means a very tiny part. And of course, like all the techniques, it's not perfect because nobody is perfect, okay? So sometimes we have relatively low sensibility, sometimes, not ever. And sometimes it can appear some fluorescence depending on the material we are studying. We can solve this. I think I don't have time enough to explain, but we can solve these problems quite well. So just a very simple thing to explain how it works. Okay, we have a Raman spectrophotometer which has a laser in it. Just don't panic. A laser is very soft and gentle. Do not really destroy anything, okay? And this laser illuminates the sample and gives us information about what is lighting up. And how does it do this? Well, because, me, everything in the universe is about molecules and atoms. I think you already know this. And surprise, surprise, atoms are moving, vibrating, okay? Even in your body right now, or your chair you're sitting in, okay? So this vibration is what this light is looking at. How do they vibrate, right? And they stimulate this vibration and give us information about this. I know it's a weird concept, I know, but it is like that. So we receive this information in a kind of a barcode. As you see in this computer, this is what we call a spectrum, okay? And these are the energies of these vibrations of atoms into molecules. In the lower part, you can see 3 different spectrum. which tell us what kind of pigment we have. For example, hematite, which is iron oxide, very common in prehistoric paintings. Or pigment, which we have found, for example, in Egypt, in some cultural heritage from Egypt. Or cinnabar, and we can distinguish perfectly well one from each other. But let's go to the inks. I think you are more interested in. Okay, this lack of information is really the motivation why a chemist is between all of you. And the point is that we can identify molecular compounds in metal gall inks. And these are structure of complexes. This is a chemical word, but it's true, believe me. Two, because dating and location, and this is very important for you. Well, actually, it's very important for everybody, but I think especially for you. And as I said before, conservation of manuscripts regarding this degradation. As you said, degradation by the ferrogallic inks are very important in papers. So let's begin with some examples to see what can we do with this technique. The first of all is a black inks study from an invoice from the Historical Archive of Asturias, Spain. This invoice is from 1835. And you can see the points in the invoice. These points are pink or yellow, which means the pink of ink analysis, and the yellow, the analysis of the paper points analysis. Right in above, you have the image, the microscope, because what we've been using in this one is Raman spectroscopy coupled with a microscope. So we can see through this microscope first the sample, and then we make the analysis. And at your right, you can see this barcode called spectrum, where we have the paper in blue, and then we have the dark blue is the invoice ink. We wanted to compare it to an ink coming from a missile, right? To see if they were the same. So we made a difference between them because you think it's the same ink. It may appear it's the same ink, but it is not. They have differences, okay? So we can really distinguish very similar inks, but we do know they are not the same. So this is very important, for example, for corrections. Does this correction was made by the same ink or not? I'm talking about ink because you have to say if it's the same author or not. This is your part, okay? Okay, let's gonna follow this. Black inks in the book Curiat and Guelpha. Maybe it sounds to you. This is from the 14th century, coming from the Spanish National Library. Here there's another spectrum. I have said by now that we have a spectrum of one ink, but sometimes, actually, almost always, you have a mixture of things, mixture of compounds. Can we solve this perfectly well? Here you have an example. In this two spectrum from the same book, we have different bands which are telling us what kind of composition these inks were. You have carbon black, then we find iron gall ink, and we also find bicarbonates, carbonates, and sulfates. So it's a complex mix, and we can solve it. We do know what this ink has inside, all right? Sometimes the spectrum are not very good. This sometimes happens. I mean, it's not perfect. Like you see it in your left, this is spectrum, it's not very good. It has a kind of inclination. It's what we call a background, okay. But we can correct this using mathematical techniques. The first of one, baseline or smoothing. The baseline makes this spectra to come to the horizontal line. You see the black one in the back of the right image. And once you have done this, for example, in this case, you see a little lines in this blue. You see it? This is what we call noise, right? It's provoked by different physical effects. So if we wanted to take off this noise, we make what we call smoothing, okay? We make it more gentle, the spectrum. So we can differentiate there, then, bands that we couldn't see before. And so we, for example, can recognize the bands of the paper right there. So just with the natural spectrum, we can do all the things I have related. But sometimes when the spectrum is not as good, we can even still working with them, making an after processing mathematical program. Let's gonna see some other example. This is a Raman analysis of documents from Seville from the 18th century, coming from Valle. Thank you. So we were studying this, and there was something suspicious for Valle. She was thinking about, okay, is the signature really made by the same ink? Because as you can see here, there are two parts of the signature. One at the right is quite black, it's very black. And at the left, you have like a very soft brown ink. Is it the same or not? Let's gonna see it. So we made a spectrum, a Raman analysis in both parts. And we saw that in this case, it is the same ink. Probably they have left ink on the pen and then just take the pen into the pen again. So, and it's still right again. So in this case, the ink were exactly the same. But in the same documents, different documents from the same Sevilla documents from the 18th century, we had different inks. Not all of them were write it down with the same composition ink. What does it mean? Well, I don't know. You should say that. Probably different times or different hands or different moments. So all this analysis show us that although the documents were dated more or less in the 18th century, the inks were all different. Right. In this case, there is a signature, Manuela, by one side, if you can see it, with a strong black ink. And then a signature from what we call the pagador, the people who paid, because this was a kind of invoice, okay. You can see that actually when you visually, you have different color. It could be happen like before, different color, but the same ink, same composition. But in this case, the inks were a little bit different. And we can distinguish that. So why? Maybe concentration of each component of the chemist's recipe, or they have left one ink and had to make a new one, maybe. So in that moment, or probably the signature from one is a little bit later than the other. No, were not made at the same time, maybe at different times, right? And this is another example where we studied different parts of another signature from the same documents and from Sevilla. And we discovered carbon black and iron gallic inks. It's very usually that you can find carbon black joining for gallic inks, because it seems that this carbon black was making more brilliant the ink. So, as I said, the composition of inks are not easy. They can be really complicated, okay? And now another application of Raman, which I think might be from your special interest, is what we call a mapping. This is an example what a mapping is. In this case, in this kind of invoice, we had a number, as you see, 002, with the second 0 was like corrected. And we wanted to know if this correction was made at the same time or it was made later. Okay. So we were thinking, we made what we call a mapping. A mapping is you take an area of a study, in this case the 0, and you make a Raman analysis point by point, covering all the area. It's like if you were passing through point by point, in this case, approximately 3,000 points of analysis. It took us 2 hours and 30 minutes to make this. Yeah. Okay, yeah, I think it's worthwhile. You're right, yeah. And so the first image on your left is the natural one, and the second at your right is the image of the area of one of the components of the ink, which tell us how to explain if this is all the same ink. If there were 2 different inks, we would see the one with one color and the 0 with another color. In this case, we have the same color in everything, so it's the same ink. They have been using the same ink to make the correction. Probably, and as we can see here, PC1 is the component 1 and the component 2, because it makes a different analysis component. In this case, it's the same ink and probably make at the same very moment. At the same moment the correction was made, probably. Because there are no difference in composition. But otherwise, if the composition would be different, we could see the 1 in one color, number 1 in one color, and O in another color. So we could be distinguishing perfectly well the correction, right? Some other examples of what we can do. Okay, here are documents from the 19th century, coming from Emilio Casteller letters. He was a politician and a writer too. And this is very interesting. I'll tell you why this man is so interesting for us. Because this man received letters from all around Spain. Okay, and you say, so what? So we can study the inks coming from different parts. Are the inks the same everywhere or are different? So we are still studying this. This is an image where you can see how we study in situ these documents. As I said before, we don't touch the sample to make this analysis. It's just illuminating by the laser. This is one PhD student we have in Madrid studying these documents, and the equipment is not very hard. It's not very difficult to move. It's quite easy. So we've been studying this and different comparing, and then we discover, for example, different inks using copper instead of iron. So with different complexation, I mean this different composition, chemical composition, and different polyphenols, which are different molecules, just to know. This let us know we are working on it because it's a huge work. We have a lot of documents and we have a lot of analysis to do. But we want to make a map, as you see here, with different composition inks in different parts of Spain. Because the composition coming from Sevilla, for example, it's not the same coming from Barcelona or from Canary Island. So she's working on it as a student, PhD student. What we want to do is to make a kind of a library of inks, because we can differentiate very well which ink is composition and which are coming. Just think it's not the same if you're making an ink with different components in the south of Spain or in the north of Spain or where they have been bought. So, but how do they prepare the iron gall inks, which is the most common ink. I said sometimes they use different metals, but I have to say the most common ink is iron gallic. So they use, and we know it because there are some recipes written. They use oak galls, metal salts, gum arabic, and sometimes some other ingredients. The preparation depends on the recipes, but these are the components I have related. The oak galls coming from the tree, which have inside the tannins, is a huge molecule, you see there. The metal salt, which can be iron sulfate, copper sulfate, or zinc sulfate. These are the main interesting metal salts. And gum arabic. Gum arabic just as a binder of all of this, okay? And what did they use? At first, I thought that they used only water, but actually, they use wine. Really? I mean, that was a surprise for me. So, this solvent, and probably lemon or vinegar or what they had in their kitchens, it's going to make an ink. And they had, you know why these inks are quite different then, huh? And sometimes they had some other ingredients like indigo, kermanic, alum, epsonite, wormwood, nib sugar. Okay, I mean, there are a few things to have in. I guess it's supposed how inspired this ink maker was. Okay. And we had a project we are doing, a project preparing in the laboratory, trying to reproduce these recipes, trying to use an iron gall inks with different recipes we have found. This is very interesting because we are using pure compounds. We work as a chemist, so we use pure compounds. So we can compare the results and these results with the real inks coming from original letters, for example. Well, this is a graphic of different compounds of these ingredients I've told you before. So if you change the ingredients, it changes the spectrum. So that's why we can differentiate, we can distinguish perfectly well from each other. And there's an image. How do we make some test? How do we have spectrums from this laboratory analysis and take the spectrum of all of them, okay? So we can compare. Probably for you, it seems the same spectrum, but I'm telling you these are not the same in between, okay? We can have, we can see differences, movement and shifting of the bands, different wider of the bands, everything that is in there is very interesting for us and tell us information about what is inside the chemical composition. And of course, degradation of paper by iron gall inks, which the pH is very interesting, very important. Very acidic pHs are degrading the paper or the substrate or the materials where the ink are. So the effect of pH is very interesting, and that must be a very interesting part of a study to see how to conserve as much as we can these documents. So we're on this study. For example, we have seen in different tests coming from pH very alkaline, which is 10, to the most acidic, which is pH 2, although pH 1 is more acidic, 2 is very, very acidic. You think the pH of our stomach is pH 1, so very acidic. And you see the spectrum in green is the spectrum of a paper, so you can see how it degrades when you change the pH. It disappears. So that's what the gallic ink does into the support. And how we can study all these things, the composition. With Raman, we can know what is inside, but of course, it is very interesting to have complementary techniques, because these complementary techniques makes more complete information, although Raman has quite complete information too. But for example, the Gallic, the tannins are very well seen by Raman, or Sirs is a part of Raman, which I'm not going to talk today because it's too much, I think. Metals, we can see them by XRF or EDX, and infrared for the gum Arabic. But although it's more complementary, because Raman spectroscopy is quite complete. That's why we have chosen this years ago. From years ago, Raman has been using for cultural heritage, and actually we've been studying a lot of things with Raman, a lot, from archaeologies, Egyptian samples, pigments, inks. So that's why we choose it as the main spectroscopy technique. And with this, I'm finishing. So thank you very much for your attention. Any question? No? Is it so clear? Yeah. Go.
Very interesting. Thank you very much. I'd like to know, with your analysis, is it possible to establish a period and to put different elements in chronological order, not only comparing two similar inks, but making some arguing some ideas about the period depending on the decaying of some specific elements, something like
Well, we have a very good thing here, working with you, with philologists, because, for example, the letters I have told you before from Emilio Castellaro all were dated. So if you have the date in the letter, you can make a lot of a spectrum or analysis from the same data, and you can have a very good reference. Or are you talking about carbon analysis?
Something like this. I'd like to know if it is something similar to carbon.
No. Okay, carbon analysis is interesting for a very large amount of years, because it has a very big error, so of 100 years.
On other elements related to the period where the ink was used, so comparing the different inks and we have to know
Right, yes.
Specific period.
That's right.
Sometimes we use letters just to date something we don't know specifically, but the ink is the same, used, or paper, used writing letters, so we
Right.
arrive
That's the point.
Yeah.
That's what we are working with, because we have a good thing. For example, I've been working also with prehistoric paintings, but there are no ages, so we cannot date it. Just a stylistic, but you know, sometimes it's very hard, even for archaeologists to say if it is that period or not. But here, you have letters who are talking to you. They are telling you this letter was written in the 16th century, right? Yeah, so that's what it's very complementary, because we can make a library of inks in a period, and we can do really make it, because, for example, if the Gum Arabic was coming from the Arabic Peninsula, or if the compounds, the metal compounds, are coming from, it seems, Great Britain, or if they are different, so they are coming from different parts, so we can relate it with the data you have. So yeah, I think we can do it. Kind of indirect, not as you thought with carbon analysis, MCE, but just an indirect way of doing, making a library of data and inks at the same period.
It should be used by everyone using the digital infrastructure.
Right. That's what we are pretending, to make a library open to everybody, to see if you have an ink and you know this composition, you can go there and to see related to which year or century it is, because the inks are really different from the 18th century or the 19th century, or of course the modern inks, which are completely different from those you are studying. So yes.
Sometimes they use the same ink, like even if they were working different geographic areas, because they had the recipes, and so they can exchange.
Yeah, but yes, but no. Because if you have the same recipes, it's like the kitchen. You have the same recipe here in Italy and United States, but are you using exactly the same compounds? Because the flavor in United States probably it's not the same flavor as you have here. So the recipe might be the same, but the compounds are not, and we can distinguish this. So, yeah, it's very interesting. I think we can make a very good relation between philologies and chemistry. You're welcome. Yeah?
You might talk about it.